All right, let's just jump right into this explainer. Today, we're going to explore one of machine learning's most intuitive, elegant, and frankly, easiest to understand algorithms. We're unpacking the K-nearest neighbors algorithm, or KNN for short. But instead of getting instantly bogged down in complex math or dense computer science theory, I actually want to start by imagining a super familiar everyday scenario that you've probably experienced yourself.
Picture this. You just moved into a brand new house, in a brand new neighborhood. How do you decide which local internet provider to choose? You aren't going to sit there calculating complex technical coverage maps, right? You're definitely not analyzing signal frequencies or infrastructure layouts. No, you do something way simpler and far more practical.
You literally just walk over and ask the 5 closest neighbors on your street what they use. If 3 out of those 5 say they use provider A, well, you're going to go with provider A. You just pick the majority favorite. Boom. That right there, that exact logic of relying on the people closest to you is the absolute foundation of the algorithm we are unpacking today. It really is that simple.
So, here is our roadmap for today. 1. Meet your new neighbors. 2. The lazy learner algorithm. 3. Tuning the K parameter. 4. Pros, cons, and limitations. And finally, 5. Real-world applications. Let's get into section 1. Meet your new neighbors. The basics of KNN.
So, way back in 1951, these two researchers, Evelyn and Joseph Hodges, actually formalized this exact principle. They created KNN as a supervised learning algorithm, which just means it uses labeled training data to make its predictions. And the whole thing operates on one incredibly straightforward rule. Things that are alike naturally tend to physically cluster together in space. If you want to know what a specific data point is, you just look at the data points sitting right next to it.
Now, what's really wild is how elegantly KNN handles 2 totally different types of machine learning tasks. If you want to categorize something, like, say, predicting if an email is spam or not, KNN just takes a majority vote of those closest neighbors. That's classification. But what if you need to predict a continuous number, like the price of a house? Well, KNN simply calculates the mathematical average of its nearest neighbor's values. That's regression. It is incredibly versatile.
Moving on to section 2. The lazy learner algorithm. Let's look under the hood. I absolutely love this term. In the machine learning world, KNN is famously called a lazy learner. Unlike those hard-working traditional models that spend hours crunching data to build explicit equations during a training phase, KNN literally does 0 work during training. None. It doesn't learn mathematical coefficients or weights. It just takes the entire data set and simply memorizes it. The training data is the model. Because it's a lazy learner, it saves all its brain power for when it actually matters, prediction time. When a new query point is finally presented, the algorithm wakes up and fires off these 3 logical steps on the fly. First, it measures proximity to the new point. Second, it identifies the closest neighbors. And third, it aggregates the results to give you your answer.
To pull off that first step, measuring the proximity, it leans heavily on some classic math you probably remember from high school geometry. The most common metric is Euclidean distance. It just calculates the literal physical straight-line distance between 2 points in a feature grid. The golden rule here? A smaller distance value simply indicates a higher similarity between the 2 instances.
Put it all together, and it forms this slick 8-step process. You start by selecting K and, this is huge, scaling your numerical data so the really large values don't just completely drown out the smaller ones. Then a new query arrives. The algorithm wakes up, computes the distance to every single stored point, sorts those distances from smallest to largest, grabs the top K neighbors, tallies their aggregate vote or average, and boom, outputs your final prediction. And it does this whole song and dance every single time a query is made. Which brings us to section 3, tuning the K parameter, the balancing act. This is where we see the real inherent tension of the algorithm. It's quite the balancing act. If you increase K and ask too many neighbors, your decision boundary gets super smooth, making it way less sensitive to random noise. But push it too high, you get underfitting. You completely miss the important local details. On the flip side, if you decrease K, like just asking one single neighbor, you get highly complex, flexible boundaries. But that causes overfitting, where your model just wildly overreacts to random noise in the data.
So you've got to find that sweet spot between the 2 extremes. A classic rule of thumb in data science is set in K to equal the square root of n, where n is your total number of training samples. Oh, and pro tip, you ideally want to pick an odd number. That way you avoid annoying tie votes if you're trying to classify something into 2 distinct categories.
But wait,
Alongside deciding your K, you also have to choose how you measure that distance. While Euclidean is your go-to for straight lines and continuous spatial data, it's not the only game in town. You might swap it out for Manhattan distance, which calculates a grid-like city block path, especially when your data has high-dimensional or grid-aligned features. Or you could use Minkowski, which is just a generalized formula you can tweak based on exactly what your data needs.
Next up, Section 4, Pros, Cons, and Limitations.
Before we get into the pros and cons, how do we even know if the model is doing a good job? Well, we use standard evaluation metrics. For classification, we're looking at accuracy, precision, recall, and the F1 score, which is great for handling imbalanced classes. For regression, we use metrics like mean absolute error or RMSE, root mean squared error. RMSE is fantastic because it severely punishes the model for making huge mistakes.
When we really evaluate KNN, the trade-offs are pretty stark. On the plus side, you get incredible simplicity. It is highly interpretable. You can easily explain why a prediction was made just by pointing to the nearest neighbors. It also has instant learning and supports multi-class problems right out of the box. But the limitations? They are heavy. Because it's a lazy learner, it will absolutely devour your RAM to store all that data. Plus, computing distances for every single new query makes it painfully slow at prediction time. And as we mentioned, if you forget to scale your data, your large numbers will just completely overpower the smaller features.
But honestly, the ultimate villain for KNN is this ominous-sounding phenomenon, the curse of dimensionality. Listen to this. KNN works beautifully with just a few features, but as you add more and more features to your data, you enter high-dimensional space. And in high dimensions, something mathematically bizarre happens. All the data points become almost equally distant from one another. If everything is the exact same distance apart, the entire concept of a nearest neighbor literally becomes meaningless.
Finally, Section 5, Real-World Applications.
So, knowing all this, where is KNN actively working behind the scenes in your life right now? Well, when a streaming service suggests your next favorite movie, it's often just finding users with similar watch histories, your viewing neighbors. In medicine, doctors use it to compare a new patient's lab results to historical records to predict health risks. It's used in handwritten digit recognition by comparing pixel patterns. It's even used in credit scoring, evaluating your loan application by assessing the financial behavior of the most similar past borrowers.
Which brings us to a pretty wild thought to end on. For all our massive advancements in complex, deep learning AI, you have to wonder, how much of your daily digital life is still being shaped by an algorithm that's essentially just asking the neighbors? It just goes to show, sometimes the most powerful predictions don't come from a magical black box. They come from simply looking at whoever's standing right next to you.